Welcome to the bisection method. So the idea here is we are going to repeatedly use the intermediate value theorem to find a root or to approximate a root of a function. So we will repeatedly use the intermediate value theorem . I apologize if you can hear my daughter in the background. So we will repeatedly use the intermediate value theorem to estimate a root of a function. And essentially what we will do is we will take, if we have a function and we know that it say starts as negative and ends as positive, somewhere in between, if it's continuous, then somewhere in between, I should specify of a continuous function. And somewhere in between those two values, it must cross the x-axis. So what we will do is we will split our interval. So here's our closed interval. We will split it in half. And either it crosses the x-axis before that, it crosses after, or it does both, right? But what happens if this value is, if on that line we're negative, so if we wind up down here, then we know that we have to cross the x-axis somewhere between the middle and the last point. On the other hand, if it were positive value at that middle, then we would know that we'd have to cross somewhere in the first half. And then we just repeat the bisection method over and over, this bisection over and over and over again, slowly narrowing our way in. It looks like I didn't actually finish this. So we're going to use the bisection method to approximate so we're going to use the bisection method to approximate the root of f of x equals 2x squared minus 5x plus 1 that falls between 0 and 1 to 3 decimal places. Now, clearly, we could use the quadratic formula to solve this or complete the square and get the more precise value. But it will probably involve radicals, possibly not. And so this way we can at least approximate it. Although once again, the approximation you would probably want to use a calculator for. So what we will do is the first thing we need to check is that between 0 and 1 of those values is positive and 1 is negative. So we're going to check f of 0. Well, if we plug in 0, we have 1. And f of 1, if we plug in, we're looking at 2 times 1 squared minus 5 times 1 plus 1. So 2 minus 5 plus 1, we are looking at negative 2. So, and then we also know that f is continuous. On the whole real number line, it's a polynomial. So more precisely, it's continuous on from 0 to 1. So in this case, then, we know that whatever we're doing at 0, our function is positive, and at 1, our function is negative. So we know that somewhere between 0 and 1, we are going to cross that x-axis. So the first thing we're going to do is we're going to split our interval. So this will be at 0.5. And we're going to figure out, are we above or below the x-axis? So this is at, here we're at 1. So we need to figure out, are we above or below the x-axis when x equals 0.5? So we're going to split the interval. So we'll have our left endpoint was 0. Our right endpoint was 1. And so the middle was at 0 plus 1 divided by 2, or 0.5. So this is our x values. And now our y values. The main thing we have to keep in mind is that that left endpoint, our y value is positive. Our right endpoint, our y value is negative. And then if we plug in 0.5, we are looking at 2 times 0.5 squared minus 5 times 0.5 plus 1. So 0.5 squared is 0.25 times 2. We are looking at 0.5 minus 2.5 is negative 2 plus 1. We are looking at negative 1. So we have a negative value. So again, we have a negative value in the middle. So if we think of our picture, here we were positive, here we were negative, and in the middle we are also negative. So no matter what's happening between 0.5 and 1, we know because of continuity, it's somewhere between 0 and 0.5, we must switch, right? So we want the ones of opposite signs. So we have a positive and a negative, opposite signs. So this will be our new interval. So our new interval will be from 0 to 0.5. And then we will just repeat this over and over and over again. So now looking at our new interval between 0 and 0.5. So we have our left. I'm going to just rearrange this. I'm going to put the middle in the middle now. Left, middle, and right. So we just figured out that we should have a left endpoint of 0, a right now of 0.5. So this is our x values. For y, we're positive at 0, negative at 0.5. So now the middle that we will work with we will do 0 plus 0.5 divided by 2, and we get 0.25. So we will plug in 2 times 0.25 squared minus 5 times 0.25 plus 1. And if we solve that, we wind up getting negative 0.125. So again, this is negative. So we want where they switch signs. So from that middle to the right side, we kept the same sign. There's no guarantee we cross the x-axis. But from the left to the middle, to go from positive to negative, we must cross the x-axis. So somewhere in this interval, we must cross the x-axis. So now we'll have a new interval between 0 and 0.25. So from 0 to 0.25, actually I'll stick with green for that. So the new interval came from our green. We'll go from 0 to 0.25. And now we go again. So in the middle of those, we will do 0 plus 0.25 divided by 2. And that's 0.125. And now we will plug into our function. So if we do 2 times 0.125 squared minus 5 times 0.125 plus 1, and see what we get. This time we get 0.40625, so we have a positive. So again, we had a positive y value at 0. We had a negative y value at 0.25. And at 0.125, we are positive again. So I don't know if we switch signs between 0 and 0. Well, we don't switch signs from the ends of 0 and 0.125. So we don't know if we cross the x-axis there. But by the intermediate value theorem, we must cross the x-axis going from 0.125 to 0.25, we switch from positive to negative. So we must cross the x-axis here. So now on the left, we will do 0.125. And on the right, we will do our 0.25. So this time around, we're positive and then negative. And if we go by the middle here, we would do 0.125 plus 0.25 and divide by 2. And so we are looking at 0.1875. And then we need to figure out the y value at 0.1875. So I'm just going to do f of 0.1875 is equal to, and see what we get. And we get 0.132 ... So we get another positive. So this means this time around, again, we must change where we switch signs. So we go from positive to negative y value. So we must cross the x-axis here. And this time around, our x values, we are looking between 0.1875 and 0.25. Again, for y values, we're switching from positive to negative. So if we look in the middle between those, we will do 0.1875 plus 0.25 divided by 2. And that puts us at 0.21875. And if we find that y value, we are now looking at, a y value of 0.0019. So once again, still positive. I realized I forgot to change colors here. So this should have been all in a new color here. let's say we were in red. So at this point, once again, we switched from positive to negative, going from the middle to the right. So we must cross the x-axis here. So now our two endpoints, our x value, we are looking at 0.21875, and our right value is 0.25. So we already know at this point that we are looking at 0.2 something. It takes a while to narrow down to multiple digits for the x value. So our midpoint, we would do 0.21875 plus, oh, I should do this in another color again, I apologize. So for a midpoint, we would be looking at 0.21875 plus that 0.25 divided by 2. And we wind up getting 0.234375. If we take that y value, so our previous ones, we were positive and then negative. If we find the y value at this value, we have f of 0.234375. And we wind up getting negative 0.06 something. So we wound up with a negative. So this time around, we have switched somewhere between our beginning and middle value. So we must cross the x-axis somewhere in here, between 0.21875 and 0.234375. So our left side is at 0.21875. Our right side is this 0.234375. We are positive on the left, negative on the right for our y values or for our function. Again, find our new midpoint. So we have our 0.21875 plus 0.234375. Divide that by 2. And we are looking at 0.226565. If we plug that in, to our function f, we wind up getting a negative 0.03 something. So we land on a negative. So once again, we are somewhere where we switched signs. So we must cross the x-axis here. So we have a left side now of 0.21875 and a right side of 0.2265625. So we're getting awfully close. We've certainly narrowed down our window. In fact, we might just stop once we get down to 2 decimal digits. You can see that this process can go for quite a while. You can certainly program into Excel to have Excel do this work for you. But for now, if we just check, so if we find our midpoint, we have 0.21875 plus 0.2265625 divided by 2. And we are looking at 0.22265,625. If we find that function value, I'm not going to recopy that. Again, I realized I just forgot to change colors. So if we find this, we wind up with this is equal to a negative 0.014. So again, this is negative. We started with a positive, ended with a negative. So we must cross the x-axis between these. So now we know that we are between 0.21875 and 0.22265,625. And we know that our root lands somewhere between these. I still only have one decimal place at this point, right? Our left side is 0.21 versus 0.22. So we would have to keep going for a while to really narrow down further. I think I will stop here though. So the root is somewhere in here. And to get 3 decimal places, so to get 3 decimal places, we would have to keep going until the left and right sides match for the first 3 decimal places. Once you reach that point, then you know that the first 3 decimal places would have to be whatever those 3 were. So this is the bisection method. This problem you would have had to have kept going for quite a while. Any ones I give you, I intend to be much shorter. You don't have to keep going over and over and over and over again for 10, 15, 20 tries or bisections. But there's no guarantee whenever you start just a standard problem that you will be able to hit the approximation you wish within a couple bisections. Right, so that is the gist of the bisection method.